Welcome to the course on Principles of Reactive Programming. 1 year ago, when I finished the course on functional programming, many people asked me for a second course on more advanced material. At the time, I was too flat out exhausted to consider anything of the kind, but now, 1 year later, there is a second course. But the topic is reactive programming. So why this topic? 3 reasons, really. The first is that reactive programming is becoming ubiquitous. Nowadays, if you write any web service or mobile app, or really any large system with a real-time component, then knowing the reactive programming techniques is essential. The second reason is that reactive programming really builds on functional programming. In fact, we will spend the first 2 weeks of this course with some of the more advanced concepts of functional programming, which then will lead naturally into the reactive programming content of the course. Third, I'm really happy that I could draw on the help and expertise of 2 of the masters of the field, namely Eric Meyer, who is the inventor of RX, the Reactive Extensions Framework, and Roland Kuhn, who is the lead of the akka library for actors concurrency, who will both co-teach the course with me. So, let's get started. Reactive programming describes a set of programming patterns and techniques that have become increasingly important over the last years. And the reason for that is mostly driven by changing requirements. 10 years ago, typical large installations would have tens of servers. Response times would be measured in seconds. There would be maintenance downtimes, a couple of hours per month, say, and data volume would be measured in gigabytes. Nowadays, a large server installation or cloud installation would have thousands of nodes. Users expect sub-second response times in the milliseconds. There should be no maintenance downtime. System should be available 24/7. And our data volume has easily reached the terabytes and is going into the petabytes. So these new requirements also need new architectures. The classical architecture is epitomized by something like the Java Enterprise architecture. It consists of managed servers and application containers. What you see now is more and more a shift towards so-called reactive applications that are event-driven, and that makes them also scalable, resilient, and responsive. The Merriam-Webster dictionary defines reactive as being readily responsive to a stimulus. What we mean by that in the world of software systems is a system that can react to events, so it's event-driven. And the system should also be able to react to changing amounts of load, system load. That means it should be scalable. Furthermore, such a system should be able to react to failures, and we call that resilient. And finally, and probably most importantly, the system should react to its users. It should be responsive. Now, being event-driven is a technical property that enables the properties of being scalable and being resilient. And all 3 properties together enable systems that are responsive to their users. So let's start with event-driven. Traditionally, concurrent software systems were composed of multiple threads communicating with shared and synchronized state. That led to a very high degree of coupling, and also such systems were hard to compose. Event-driven systems, by contrast, are composed from loosely coupled event handlers. Events in such a system can be handled asynchronously. They do not incur any blocking. And because there is no blocking, that means that typically resources can be utilized much more efficiently. The next property of a reactive system is being scalable. An application is scalable if it's able to be expanded according to its usage. And typically we distinguish 2 directions of scaling. There's scale up, which means we make use of parallelism in multi-core systems, which become more and more common in computers today. And then there's scaling out, which means we make use of multiple server nodes, often in a data center or in the cloud. Important for scalability here is always to minimize shared mutable state, because we will see that that actually has implications on the ease and the efficiency of scaling. Important, furthermore, for scaling out is the property of location transparency. What that means is that it shouldn't matter where a location is located. It could be at the same computer as a client or at some other computer across the internet. The functionality should always stay the same. The other important property for scaling out is resilience, because once you have multiple nodes, some of these can fail and your system has to cope with that. The third property of reactive system is resiliency. An application is resilient if it can recover quickly from failures. Such failures could be software failures, such as throwing an exception, or hardware failures, a computer going down, or maybe connection failures, internet connection going down. Typically, resilience cannot be added as an afterthought. It needs to be part of the system design from the beginning. Important techniques for constructing resilient systems are keeping your components loosely coupled, having a strong encapsulation of mutable state, and having pervasive supervisor hierarchies. Finally, an application is responsive if it provides a rich, real-time interaction with its users, even under load and in the presence of failures. Responsive applications can be built on an event-driven, scalable, and resilient architecture. That doesn't automatically lead to a responsive application. You still need to pay careful attention to algorithms, system designs, including back pressure, and many other details. But being event-driven, scalable, and resilient are important, some would argue even necessary, building blocks to arrive at a responsive application. Now let's take a closer look at events and event handling. Of course, event handling is not new. It's traditionally been done using callbacks. A common form of callbacks is found in Java in the subject-observer pattern. So you see an example here. We can define a class counter that extends a class called Action Listener, which is part of the Java Swing framework. And then what the counter would do, it would register itself with an event source. In this case, the event source is a button. So it would say add action listener this, and that would register the counter itself at the event source. Then the event source would call whenever there's a new event, this method action performed. So that's a callback. You register yourself to be called back here. And when the callback comes, there's an event that gets triggered, which gives you details about the event. And then every time that gets triggered, you perform an action, like increment the counter by 1. Now, this is the common model that I guess most of you have already seen today, but it's also a model that has quite a few problems. So the first problem is already apparent in the type of this action performed method. Its return type is unit. So that means to have any effect at all, the action performed method has to have a side effect. In this case, the side effect is on the variable count. So a design using listeners and callbacks naturally leads to shared mutable state. The second problem is that it's very hard to construct higher abstractions out of simple listeners, so event handlers have a hard time being composed. And in summary, all this leads quickly to what has been called callback hell. So that means applications that essentially consist of a big web of callbacks that are very, very, very hard to track and understand. So how can we do better? So the idea that is promoted in this course is to use fundamental constructions from functional programming to get composable event abstractions. In particular, some of the core principles of this course is that events should be first class. They are often represented as messages. Handlers of events should also be first class, so that complex handlers can be composed from primitive ones. So here are the topics that we are going to cover in the next 7 weeks of this course. We're going to start this week with a review of functional programming, about to the degree that you have already seen it in the first course of on principles of functional programming in Scala. But we are also going to introduce some new topics. In particular, we're going to cover an important class of functional patterns called monads. However, reactive systems are not typically described as pure functional programs. So next week we are going to open up the paradigm of pure functional programming and combine it with the more typical world where you have mutable states and non-deterministic computations, including events. After these two more preparatory sessions, we apply what we know to reactive abstractions. We first cover how to abstract over events that will lead us to futures, then how to abstract over event streams that will lead us to so-called observables. We will then look at message passing architectures where the nodes are actors. We will look at how to handle failures, including the concept of supervisors. And finally, we will look at scaling out to distributed systems, looking at distributed actors. The course is given by 3 lecturers. I will cover the first 2 weeks. Eric Meyer will cover futures and observables. That's week 3 and 4. And finally, Roland Kuhn will cover actors, supervisors, and distributed actors. As prerequisites, you should have a solid grounding in functional programming. Ideally, you have followed the principles of functional programming in Scala class on Coursera, but if you know some other functional language, the switch should be rather easy.